later what I mean by symmetric. This kind of problem can be encountered in the machine developed by machine to store renewable energy. So in the following, our contact problem will be expressed as a minimization problem in order to use some optimization techniques to converge faster to the solution. And also numerically, we will use the interior point method in order to solve our optimization problem. And because it has several advantages. So I will start with some definition. Here we take a body omega in its initial configuration, and if we apply a force or an responsive displacement, it will become phi omega. Phi will describe the transformation of the body. And if we phi omega, it's the body and its actual configuration. And if we take and if you take a material point big X, it will become small x, and our unknown in the following will be the displacement field U, which will be small x minus big X. For a matter of time, I will consider only the linear elasticity case, but the finite deformation or large deformation case can be also solved by our algorithm. So I will start with, for example, a sigmoidal problem, which is a contact between a body and a rigid foundation. Here we have equations, for example, balanced equations, and Hooke's law, for example, in the case of linear elasticity, which describes the behavior of the body. Sigma is the Cauchy stress tensor, and epsilon is the strain tensor. Here we have boundary condition, and we have also contact conditions, which, for example, the first inequality will describe the non-penetration between the body and the rigid foundation, or it can be also a second body. Gamma C is a potential contact area. Otherwise speaking, for example, gamma C, the true contact area will be included in phi gamma C. The true contact here will be included in phi gamma C. Phi gamma C, it's gamma C in its actual configuration. And here, the non-penetration, for example, we take a point X and its projection Y, and X minus Y scalar the vector, the normal vector N, must be always greater or equal to 0. And here, sigma N, which is the normal pressure at the contact, must be negative. It means that we don't have addition here at the contact area. And also we have a certain complementary equation. Now we can, for example, define admissible set. For example, we impose a derivative condition on gamma 0. We have, in the case of linear elasticity, a linear relation between the strain tensor epsilon and the displacement field, which is our unknown. We can also define a potential energy, for example, in this case of the linear elasticity, and A will have some properties, for example, continuous, bilinear, and elliptic, continuous and linear. In the case, general case, or in the case of hyperelastic material, that potential energy can be given by form, where psi is energy density function, which depends on the material. And if we define here, K will describe the non-penetration between the body and the rigid foundation, or between two bodies. And our problem can be expressed as a minimization problem, and more constrained minimization problem, the minimization of the energy, potential energy, over the set K, which describes the non-penetration. And in the case of linear elasticity, this problem also is equivalent to a variational inequality here. And by using the properties of the application, we can use Stampakia's theorem in order to prove the existence and the uniqueness of a solution. Always in the case of linear elasticity. Now I will talk about the contact between two bodies, and I will explain why asymmetric problem is necessary. Asymmetric formulation is necessary. Here we will take two bodies, omega 1 and omega 2. Phi omega 1 is the body of its actual configuration. Here we can describe the non-penetration between the first body and the second body. We'll describe the non-penetration with respect to the first body. Therefore, we'll take a point x1 and its projection on the second body, and x1 minus x bar scalar n must be always greater or equal to 0. And because we describe here our non-penetration with respect to the first body, the first one is called slave, and the second body where the projection here belongs, it's called the master body. And if we discretize our problem and use finite element method, if we choose the second body as slave and the first one as master, we will not obtain the same results as if we take the first one the slave and the second one the master. Therefore, it's a non-symmetric formulation, and the user must choose the best slave and the best master in order to obtain the more accurate solution. But we can, for example, there is a different criteria to choose the best slave. For example, if the first body has a finite mesh, or is less stiff than the second, or has a curvature, it can be chosen as a master, as a slave. But what if, for example, has a finite mesh and the second body is less stiff than the first body? Therefore, we have a difficulty to choose between the best slave and the best master, and this problem also occurs in the self contact or in the contact for the contact of more than two bodies. Hence, the need to develop a symmetric formulation or a symmetric algorithm in order to not distinguish anymore between a slave body and a master body. Therefore, the user does not choose anymore a slave and a master. Yes, we developed several formulations to make a symmetric formulation, a symmetric algorithm. For example, we use the penalty method, but here I will present a more simpler method. But before presenting the symmetric formulation, here we have the non-penetration condition with respect to the first body. Therefore, the first one is taken as slave and the second one as master. Instead of taking this this condition, we can take a weak form of this non-penetration condition. For example, here we have our minimization problem, and we will have here an integral, and we'll have here NC1 constraints. NC1 is the number of nodes at the potential contact area here. And phi I is the shape function at each point here. Of course, because here also the non-penetration condition here, the constraints are described with respect to the first one. Also, the first one is considered as slave and the second one as master. Therefore, also it's a non-symmetric. But why we use the weak non-penetration here in order to obtain more smoother results. We can, for example, make this formulation a very naive symmetric formulation. For example, here we will keep this non-penetration as considering the first one as slave and second one as master, and we will add an additional constraints here by considering the second one as slave and the first one as master. Therefore, we will obtain an additional NC2 condition. Here, NC2 is a number of nodes at the second contact area here. And therefore, we obtain NC1 plus NC2 constraints. But if we use some optimization method, like for example, active set method, with a optimization method that at each iteration activates several constraints. Here, in this case, we may have a numerical difficulty. For example, the Jacobian matrix of the constraint may be ring efficient. And we will have a problem using Newton method because the stiffness matrix will be singular. But if we use the interior point method, for example, in this paper, we can show that we will not obtain this kind of problem. And at each iteration of the Newton method, the stiffness matrix remain non-singular. And also, we prove the convergence of the interior point method in this case. Now I will talk about the friction contact problem. We have two bodies, omega 1 and omega 2, initially at contact at gamma c. We have also the same balance equations, but here we have two balance equations for the first and the second body. Also, we have a contact condition in simpler form, and in general, frictional problems, the Coulomb's criterion is often used. And here, this tangential stress, the tangential stress vector is opposite here at the contact because the actual reaction low. And here, the Coulomb's criterion, we have this inequality. Here, the module of the stress, the tangential stress vector will always be less or equal to the coefficient of friction mu times the normal pressure here at the contact. For example, if here we have a strict inequality at a point, let's say here, then the two bodies stick at this point. And if we have an equality, therefore the two bodies can slip at this point. Unfortunately, the frictional contact problem cannot be expressed as a minimization problem. Therefore, we cannot use our developed method in the case where we didn't have frictional, which the developed method where we used the minimization problem. But in the following, we will see how to avoid this problem and how to write our Coulomb's problem into a sequence of minimization one. So we can use our developed method, which are based on minimization principle. Also, we have another criterion for friction. For example, Tresca criterion, where we, for example, we will take a tau, which will be called sliding limit, and here we have the same as the Coulomb's criterion, but here instead of mu sigma n, we have a given sliding limit tau here. And this problem can be expressed as a minimization problem. For example, to see that, for example, we can consider this set here V1. We have a product here because we have two bodies. Also, we have the same application as before, but here we have some also because we have two bodies. And we can consider this functional, which depends on tau, the sliding limit here for the Tresca. And also the K, which describes non-penetration. And this problem can be expressed as a minimization problem, or, for example, we have here can be as this variational inequality, or which is equivalent to the minimization of this functional G tau over the set K, the non-penetration set. G tau is given by this, given by the potential energy plus this functional. And yes, the Coulomb's criterion can be given as a sequence of Tresca problems, therefore a sequence of minimization problem. And more precisely, the Coulomb's criterion can be equivalent to the fixed point of this application T, for each sliding limit, it will give minus mu the normal pressure of the displacement field U tau. U tau is the solution of the Tresca problem for a sliding limit tau. It's the solution of this problem or of this problem. Yes, but if you remark here, the case of Tresca, we have a model vector here, and which makes this functional non-differentiable. Therefore, in order to use some optimization techniques or some optimization method, we will regularize this model vector in order to obtain a more a functional which is smooth enough. This model vector will be approximated by a function, regularized function, which is smooth enough in order to use, for example, the interior method to solve the problem. Yes, so this model vector is approximated by this eta alpha, which belongs to this family psi alpha. And psi alpha will be a set of a family of several regularized function which approximate this model vector. For example, can be C2, convex, symmetric, positive, and also satisfying these two inequalities. For example, we can give an example for a regularized function. For example, here, where alpha can be strictly positive, different from here. And then in the numerical example, this function will be used to the simulation. Yes, also we can define our regularized Tresca problem. The same equation, same problems as before, the same minimization problem, but instead of this functional, it will be replaced by this function here, where the module vector here will be will be replaced by this regularized function. Yes, if we consider our regularized Tresca problem, if we have, for example, the displacement field is sufficiently regular, then for example, if it satisfies this or the minimization problem, we will obtain a balanced equation, the same equation as before, balanced equation, and we will obtain a new frictional criterion, where here we will have a relation between the tangential stress vector and the tangential displacement field. We will see after the numerical simulation how it
5 minutes.
works. Yes, for example, the error between Tresca solution and the Tresca solution can be given by this inequality where it depends on the alpha. Also, the regularized problem also can be given by the same fixed point of the same application. Therefore, our regularized problem will be a sequence of a regularized Tresca problem. Therefore, a sequence of elimination problem which are smooth enough, where we can use, for example, the interior point method in order to solve it. And also we can use, therefore, we can modify our developed method where we didn't use friction. I will briefly here describe the algorithm. We will take two meshes. Our unknown will be the set of degree of freedom, which are the set of the horizontal displacement and the vertical displacement of each node of the two meshes. Here, this first algorithm will here we will express our column regularized problem as a sequence of Tresca regularized problem. Therefore, for each sliding limit TOCA, we will solve a test characterized problem, which will be given as a next algorithm, which will be just a generalization problem. We'll obtain the displacement field, and we compute the normal pressure, and there's new sliding, we'll obtain also the new sliding limit by the fixed point. And the problem in the algorithm converges when the error between two sliding limits is small enough. And the second algorithm is just to solve the test regularized problem. Here it's in the case of line deformation, but in the case of linear elasticity, we have just step 4 and step 5, where we form the energy, and we use the interior point method to solve the minimization problem. We used the IP opt to solve the minimization problem. For example, to see how to use IP opt for a very simple example with a simple example. For example, we want to minimize, for example, this real function where we don't have any constraints. First we have to load the IP opt library. Then for example, we define our energy here, where it's a vector of one component, because here we have a real value. We have x minus 1 square. Also, we can define the Jacobian, or in this case, it's the derivative, the Hessian, which is in this case the second derivative. We propose an initial guess, and we solve our problem by calling this function IP opt, where here the energy, the Jacobian, the Hessian, and our unknown. And we can print all this. Just present to you briefly to the example. Here we consider the contact between a body, omega, and a rigid body. Here we apply a vertical force and a several horizontal force. Here we fix our this slide. We fix it horizontally, and we are interested to plot the ratio here at this midpoint of the ratio between sigma t and sigma n. Sigma t is tangential stress, and sigma n the normal stress here. Here, for example, the theoretical relation will be the black one, and our simulation is this triangles. And for example, it's for here 0.1 will be the friction coefficient. For the real Coulomb criterion, we will have a straight line here, and then a vertical line, and then a straight line, which we call multivariate function, because for 0, for example, we have the negative values. Here we see how it approximates the Coulomb's criterion. I must point out that that also this regularization depends on the coefficient alpha. For example, if we take alpha more small, we will approximate more the Coulomb's criterion. This regularization can have an experimental justification. For example, in the case of contact between two steel bodies. And finally, here we have a contact between two bodies, omega 1, omega 2. We apply an opposite displacement here. This point can move vertically. Here it's fixed point, and here the second body can slide on its bottom. Here we have this contact between the two bodies. Here we took three friction coefficient. For example, 0, where we don't have friction, we will obtain this slide. We can see the sliding between the two bodies. For 0.1, we also see a friction sliding, and for a coefficient of friction 0.2, which corresponds to the slope of this contact area, we see that the two bodies stick together and act like the one body. I think is yes.
So, thanks, Houssam. have time for short questions.
Tout ce que tu as fait, ça généralise au 3D. Everything you did can
Yes,
be
yes,
generalized.
3D, yes, yes, 3D, yes. And 3D,
Okay.
and I want to, for example, 3D and also the columns friction. It's here we have. I presented the static case in the real life. The columns criterion depends on the path. Therefore, it depends more on the velocity than just the displacement field, but it can be given as a sequence of the static columns criterion.
You speak about symmetrization of the binary condition.
Yes, symmetry. It's for yes, symmetry. It's for this. For example, it means that if I take the first one as a slave and the second one as a master, it's the same thing as if I take the second one as slave and the first one as the master.
Why is it interesting with friction to have symmetric?
It's because in fact because if we choose the first one as slave and the second one as master, we will not obtain the same results. If we take the second one as slave and the first one as master, the user will not obtain the same results, and we have to choose between the best slave. We have to choose where we express our non-penetration. For example, here x1 belongs to this first body, therefore it's considered as slave. Then the user must choose the best slave in order to obtain the more accurate result. So, change here. Switch.
There is one question on the Zoom.
Il y a une question sur le.
Tu as accès au chat ou tu le fais à la liste? C'est le dernier message.
So,
I didn't understand your question. It's for the smoothing. Yes, the smoothing can be chosen. We can have different methods or smoothing techniques to compute our normal field. Yeah, but for the interior point method, no, it's not necessary for. It's not necessary to stabilize the contact. No.
I think we can discuss both
sorry.
after. Otherwise, session will be infinite. So thanks again.